Hi everybody, it's Mr. Lamping and welcome to another unit in our ESACS geometry course. This is Unit L. This has to do with polyhedra, which is three-dimensional polygons basically. We're going to be looking at surface areas and volumes of lots of different three-dimensional objects. We're going to look at things like prisms right here. We're going to look at things like cylinders. We'll look at cones and pyramids, those types of things. But before we begin with all that, let's start looking at terminology. A polyhedron is a three-dimensional figure whose surfaces are all polygons. You look at this, every surface of this is a rectangle of some kind. I mean, it could be a square. Down here, we see that there's a polyhedron that you can ignore the orange plane there, but you have a triangle as one of the surfaces, you have a rectangular surfaces and things of that fashion. Here's one that's sort of split open. This is called a net. It's an unfolded two-dimensional representation of a polyhedron. We've got all kinds of rectangles as well as two hexagons as what we call the bases. So let's take a look at the terminology here. So there are three basic things you need to see in every polyhedron: a face, an edge, and a vertex. So the face would be the side of a polyhedron, and it's a polygon of some kind. Over here, the faces would be the rectangles or the squares. The edges will be where the two faces meet, so the edge would be right here, right here, right there, right there, right there. There's many of them. And the vertex would be where three faces intersect. They'd be the corners, the points, where all of the polyhedron or all of the faces meet. A very famous Swiss mathematician by the name of Leonhard Euler created a formula in his work in geometry and graph theory and other types of mathematical areas. He came up with a formula called Euler's formula, and it says F plus V equals E plus 2. And it stands for that the number of faces plus the number of vertices in any polyhedron is equal to the number of edges plus 2. How he proved that, I don't know. But that's the formula that we will be using when we try to figure out certain numbers of faces, edges, and vertices. We'll look at an example of that here shortly. That's probably one of the main things you'll do in this section, homework-wise. A cross-section is the intersection of a solid and a plane. In other words, if we slice through a polyhedron, the cross-section is what we get. So kind of like if you slice through a loaf of bread, you get one slice of bread, and the shape of that slice of bread is the cross-section of the loaf of bread. Here, if we slice through this triangular prism, and that's what the orange plane is doing, it's slicing through it, we get this red triangle. That's what we call the cross-section of the solid. And sometimes we call a polyhedron a solid. All right, and then like I said before, a net is a two-dimensional representation of a polyhedron. If you cut this out and fold it on its lines here, we could create and tape together the pieces, and we could create the three-dimensional hexagonal prism with this shape. Okay, let's take a look at a couple of examples. So how many faces, how many edges, and how many vertices do these polyhedra have? So if we look at this first one, this is a pyramid. It's got one base, and it's got a vertex at the top. And that's what we will talk about when we talk about the definition of a pyramid later on. So the number of faces would be the bottom, and then 1, 2, 3, 4 sides. Because the bottom is a square or rectangle, we're going to have 4 triangles coming up to meet at that point at the top. So we've got 5 faces. The number of edges, well, let's look at the bottom first. We got 1, 2, 3, 4 edges there. Then we got 1, 2, 3, 4 edges all coming up to meet at point H. So there's 8 edges. And then the number of vertices, we would just count them 1, 2, 3, 4. And then there's a 5th one at the very top. And there's 5 vertices. Over here, we can look at this prism, and we can find the number of faces. Well, we have the top and the bottom, which would be 2 faces. Those are called the bases. And then we have what's called the lateral faces, which are all rectangles. And we've got 1, 2, 3, 4, 5, 6 of those, 1 for each side of the base. So 6 of those and 2 bases make 8 faces. Now, there's a lot of edges here. So if we look at the top first, we count 1, 2, 3, 4, 5, 6 edges, which is the number of sides of that base. We've got 6 more on the bottom, so that's 12. And then we've got a line going from each vertex down, and there's going to be 6 of those. So that's going to be 18 edges. Looking at the number of vertices, the corners, we'll see 1, 2, 3, 4, 5, 6 at the top and 6 at the bottom, making a total of 12 vertices. And we could use Euler's formula, which again is, let me double check it, F plus V equals E plus 2. We could check that formula with these numbers and verify that this is true. F plus V is 10, 5 plus 5 is 10, and 8 plus 2 is also 10. Over here, F plus V is 20, and 18 plus 2 is also 20. So it fits for those two polyhedra. Now, we want to look at this last example here. How many edges does this polyhedron have? Well, it's got 20 faces. It's got 12 vertices. Let's use Euler's formula and find out. So F would be the number of faces. That's 20. V is the number of vertices. That's 12. Number of edges, I don't know. Let's leave that as E plus 2. Simply solve that for E. So we're going to do 32 equals E plus 2. Subtracting 2 from each side, E will equal 30. There will be 30 edges for that polyhedron. And there's your notes and examples for our first section in Unit L, L1.